Hey everyone, so we're looking at section 3.5 and as you can see this section is actually going to talk about rational functions, and then towards the end we will also look at rational inequalities. So basically when you're talking about rational functions, you're basically talking about functions that are ratios of polynomial functions. So basically what happens is your numerator and denominator can both be polynomial function. Now they can be degree 0, degree 1, degree 2, or go up as high as they want in their degrees. So just some examples of what rational functions would look like. You can have y equals 1 over x. You can have something like f of x equals 2x minus 3 over x plus 4. Excuse me. So basically the idea is you should have a numerator and a denominator, or basically a function that is in the form of a over b, where again both your numerator and denominator can be polynomials. So you can kind of define it as p of x over q of x. Now, of course, if you're going to have a polynomial on the denominator, you are going to have some variable on the denominator. So you just have to make sure that your denominator is not going to be a zero polynomial, or basically your denominator should not equal to 0, right? Because anything that makes your denominator 0 will make your rational function undefined, okay? So just as an assumption for this textbook, we are going to basically assume that our function is given to us in the lowest forms, which means there's nothing common between the numerator and denominator, so no common factors, unless they're telling us to simplify the expression, okay? So another thing you want to kind of work with is when we're talking about the domain of these rational functions, we say the domain is going to be the set of real numbers, with the exception that the, let me see if I can find so when we're talking about the domain of a polynomial function, of course we're saying it's the set of real numbers. But when you're talking about domain for a rational function, remember anything that makes your denominator 0, you cannot use that in the domain of your rational function, okay? So polynomial functions we know are going to be the set of real numbers, with the exception for a rational function where you have a polynomial in numerator and denominator. Your denominator, you have to exclude any number from the domain which would make your denominator 0, okay? Alrighty, so talking about this example, y equals 1 over x, since x is in the denominator, we will say you can have all real numbers except 0. So that's the first example we are going to be talking about here, is finding the domain of this function. So we are given f of x equals x minus 1 over x squared minus 9. So let's talk about how to find its domain. So it's actually pretty simple. All you do is only take the denominator expression and set it equal to 0. Okay, so you can use the square root property to solve this, or you can actually also use factoring to solve this. So remember, this x squared minus 9 is basically in the form of difference of squares, where it factors into a plus b, a minus b. So x squared minus 9, you can actually write it as x squared minus 3 squared. So that factors into x plus 3, x minus 3. So that's where I'm getting this from. And then of course you will take each of your factors, set it equal to 0, and then get your x values, right? So add 3 on this side. Sorry. Haha. This one was subtract 3, add 3 is on this side. So your positive and negative 3's will cancel out, giving you x equals negative 3 or x equals positive 3. So the idea is both of these numbers, negative 3 and positive 3, are going to make your denominator 0. And you can do a quick check here. So just again, in the denominator, if I take x squared minus 9 and replace it with positive 3, I get 3 times 3, 3 squared is 9 minus 9, you get 0, right? Or if you used negative 3, then again, negative 3 squared is negative 3 times negative 3, which will still be positive 9. So 9 minus 9 will again give you 0. So both of these numbers make our denominator 0, which means you don't want to include them in your domain. So when you are talking about, and let's do this on a number line, right? So we're going to negative infinity here, here. If you've got positive 3 on this side, negative 3 on this side, we are basically saying our domain cannot have negative 3, our domain cannot have positive 3, but all the other numbers will be okay. So everything from negative infinity all the way up to negative 3 is okay to use. Everything from negative 3 to positive 3 is okay to use. And then everything from positive 3 to positive infinity is okay to use, as long as you're not using negative 3 and 3 themselves. So this is how you're going to write the domain. Remember, again, this is going to be written like you're writing interval notation. So we're going from negative infinity to negative 3, stop, union, from negative 3 to positive 3. Again, we stop at 3. And then we go from positive 3 to infinity, again using that union symbol. And you will notice on negative 3 and positive 3, I have used parentheses instead of brackets, right? Because again, we're not including those endpoints. So this is how you write the domain for a rational function. And this is going to be true for all rational functions. You have to figure out what numbers you include in your domain, and then you leave those out. So for R, guys, remember that we cannot include negative 3, and we cannot include positive 3, okay? Alrighty. Now, the next thing we have to talk about when we are looking at rational functions is something called as horizontal and vertical asymptotes, and then after this, we'll also actually look at oblique asymptotes as well. So when we talk about asymptotes, they are basically imaginary lines that your functions will have. So let's talk about them specifically with respect to this example here, f of x equals 1 over x. So if you look at the graph for f of x equals 1 over x, it's actually going to look like the graph you see on the right-hand side here. But let's talk in terms of vertical asymptote. So you will notice here on the left-hand side graph that this arm of our graph here is getting very, very close to the y-axis, right? So what's going to happen is, because you actually have a vertical asymptote there, and that vertical asymptote is actually going to be at the line x equals 0, because remember how we said your denominator cannot equal 0, so the domain 1 over x is going to be all real numbers except 0. So that number 0, where you don't have a domain, is exactly where you have your vertical asymptote. And that's the same thing what your graph is doing down here. You can see this arm of our graph is again getting closer and closer to the y-axis, but what it does is it gets really close to y-axis, which is the line x equals 0. So it's going to get really close to it, but it's never going to touch it, and it never crosses it. So that's actually what we mean by the line asymptote. They are imaginary lines, so when you graph your function, you don't actually see them, but your arms of your graph will get really, really close to those lines, but they, like I said, they don't touch it, and they definitely don't cross it. So you can have this happen as a vertical asymptote. You can have this happen as a horizontal asymptote, and like I said, we'll also talk about oblique asymptotes in this case. So for the horizontal asymptote, for the same function, f of x equals 1 over x, your horizontal asymptote in this case is actually going to be at the line y equals 0, which happens to be our x-axis. So the same thing, this arm of our graph is going to get really, really close to the x-axis, and this arm of our graph is going to get really, really close also to the x-axis, just on the negative side, right? So you are basically again doing the same thing. Those arms are going to get really close to the x-axis, but they will not touch them and they will not cross them. Okay? So we're going to talk about basically how to calculate these horizontal and vertical asymptotes. So let's take a look at just some more explanation here. So what they're talking about is for this function f of x equals 1 over x, we know that the domain of our function is going to be all real numbers except 0. So this is how you would write the domain for this function. Now 0 is where you have your horizontal asymptote. So what they are saying is if you plug these numbers in to your calculator and do a little table for it, so from these numbers you are actually getting really close to the x-axis from the negative side. So that's going to be this part of our graph right here, and you will see our y values just start getting really large. So the idea is as x is getting closer to 0 from the negative side, your y values are actually going towards negative infinity because they're going to start getting really large on that. And then here, your x values are getting really close to 0 from the positive side, so from the right hand side, which is going to be this part of your graph. And your y values here will actually start going up towards positive infinity. So you can actually just use a table also to verify what kind of behavior your graph is going to have. So that's kind of what they're talking about here in this little paragraph. So you can kind of read that for details. So they're saying the curve will get closer and closer to the vertical line x equals 0, which also is your y-axis, but it will never touch it, and that's what makes your y-axis the vertical asymptote. Now we can use this same idea with our horizontal asymptote. So in this case, you are actually going to get really close to the y-axis. So you are actually taking your y-axis and getting closer to 0 coming from the negative side, and here your x values start going towards negative infinity. So that's actually going to be this part of our graph that they are talking about. And then here we are getting really close to our y-axis coming in from the positive side, and as you can see our x values start getting really large, so they're headed towards positive infinity. So this will be this right hand side of our graph over here. Okay, so basically the same thing is happening, that our graph gets really closer to 0 when our y gets really closer to 0 when the x starts going towards positive or negative infinity. So that makes our x-axis as the horizontal asymptote of the graph. And they're actually also telling us that this is an odd function, so we have symmetry about the origin in this graph of f of x equals 1 over x. So this is symmetric about the origin. Okay. Alright, so now they're talking about any rational function that is expressed in lowest terms. The horizontal asymptote is determined by what value is your rational expression, approaching as your x starts going positive or negative infinity. As far as calculating the vertical asymptote goes, whatever is making your denominator to be 0, that's exactly where you are going to have your vertical asymptotes. Okay? And then just something to kind of keep in mind is that not every rational function is going to have these asymptotes. So just because they're a rational function does not mean they should by default have a vertical or horizontal asymptote. Okay? So just as a definition here, you can kind of look at this little box I have over here, but basically remember the idea is to find the vertical asymptote is the same calculation as what you did to find the domain. Take the denominator of your rational function, set it equal to 0, And whatever makes your denominator 0 are the numbers we do not include in our domain, and those are the same numbers where we will have vertical asymptotes. But when it comes to calculating horizontal asymptotes, so what happens in this case is basically you have to find out what the value of your rational expression is going to be when x gets really, really large, either on the positive or on the negative side, okay? So just to kind of get you guys started on those, we are saying to find a horizontal asymptote, we approximate the value of a rational function when x is arbitrarily large. So when we say arbitrarily large, we're basically saying it's going to keep getting bigger and bigger without any bound. So that means you just keep making it as large as you possibly can. So we want to know in expressions like these where you have a number on the top and an x expression on the bottom. So you have 500 over x, or maybe even something like negative 3 over x squared, 5 over x cubed, 2 over x minus 5. What happens? So let's take this expression of 500 over x, and whatever happens in this case is going to be the same thing that happens for the others. And what I want you to do is write that x, and do this on a calculator. So you can start by taking as x to be 9, then replace it with 99, 999, would be 9,999, and for the last one, keep writing, putting as many 9s as you can. So let's see what happens in this case. So we are taking 500 divided by 9 for the first one, and you can see that gives us an answer of, and let me write that down here. So this was 500 divided by 9, which was approximately 55.55 repeating, basically, okay? Now let's change that to 500 divided by 99, and that's giving you 5.0505 repeating, right? So 5.05 repeating. Okay, now what if we change it to 500 divided by 999? Okay, so now it is 0.500500, right? And that's going to keep repeating. So as you can see, as my denominator is getting larger, the value of my rational expression, or the value of my fraction, is getting smaller, because we started out with 55, then we had 5 for the second one, and now we have 0.500 for the third one. So now let's see what happens if I take 500 and divide it by a really large number. So I'm actually going to keep typing as many 9s as I guess this calculator will let me type. So you can see I'm typing, I don't know how many of them are there, definitely more than 10 in there. And then if I hit equal, you're actually getting this number here, 5e minus 16, right? So let's write that guy down. Maybe I'll write it here. So this was 500 divided by I don't know how many 9s, a bunch of them. And this is giving us approximately 5e minus 16, which that actually means you have 0.5, but that is raised, and I don't know if you guys are familiar with scientific notation or not, but that actually means it's the number 5 multiplied by 10 to the power of negative 16, which means after the decimal place, you are going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different zeros before you get to the number 5. So you can see when my denominator gets really large, basically the approximate value of my fraction is going to be close to 0. So with all types of rational expressions that have this form right here, 500 over x, negative 3 over x squared, 5 over x cubed, 2 over x minus 5, all of these where you have a fixed number on the numerator and the bottom is a polynomial, they are all actually going to be approximately 0 when your x gets really, really large. So this is actually what I wanted you to understand when you are doing this little calculation that I had you do with the 500 divided by the 9 bunch of 9s. Okay, so any rational expression where you have a fixed number on the top and a polynomial on the bottom, as x gets really, really large, the expression is going to get really, really small because it's going to start getting closer and closer to 0. Okay, so we are saying to approximate a ratio of two polynomials where both your numerator and denominator have an x. What do we need to do to try and simplify that? So what I'm going to do is I'm actually going to go ahead and clean up some of this so we can actually have a little bit of space to write some stuff down. Okay, so I just moved everything else to one side so that we can kind of talk about the second thing here. So basically where you have both your numerator and denominator that have your variable x in it, so something like this, what you actually do is you take the highest power of your x variable. So is it degree 1, degree 2, degree 3, whichever be the highest exponent on your x variable, you are actually going to take each term of your polynomials and divide it by that power of x. So of course in this expression you can see we have both x to the first power. So we're going to take each term and divide it by x. So you get x divided by x for the first part, 2 divided by x for the second part, then on the denominator 2x divided by x for that first one, and then 3 divided by x on that second one. So x divided by x will become 1, 2 over x will of course stay the same, 2x divided by x, here both your x terms cancel out leaving you with 2, and then you're left with 3 over x. Now 3 over x and 2 over x is the same thing like the 500 over x we just looked at. So this little fraction here will end up going to 0, and this little fraction here will end up going to 0 as your x gets really large. So that's what we're talking about. These two will become approximately 0 when x is large. So that means you will be left with 1 over 2, right? And you can kind of see that calculation right here in the parentheses. So we will actually say that the approximate value of this expression is going to be 1/2, which is basically if you were finding the horizontal asymptote for this function, then we could say the horizontal asymptote is going to be at 1/2, and then usually for horizontal asymptotes we actually write it as y equals 1/2. So this is actually how we calculate horizontal asymptotes, and of course with different types of examples our calculation can change a little bit, so we'll definitely talk about them as we get closer to those examples. So let's start with example 2 over here. So again, you are given f of x equals x minus 1 over x squared minus 9. Now this is the same example that we did in example number 1. So we're bringing back that same example, but now we're trying to find the vertical and horizontal asymptotes. So same example you saw here. So remember how we did this little factoring here to figure out where our denominator was going to be 0 and what we could not include in our domain. So we're going to have to do that same calculation here for example 2 when we start finding our vertical asymptote. So let's start with the vertical asymptotes first. So for the vertical asymptote, again, you only take your denominator and set it equal to 0, and then of course we're trying to figure out what will make that expression equal to 0. So you can use factoring like we did in example 1, or let's do the square root property just so you can see the other way of doing this. So you can set that equal to 9. To get rid of the square, of course, we are going to use square roots. So you will end up getting x equals plus or minus 3. Okay? So remember, these are the same numbers where your denominator becomes 0 and we do not include it in our domain, positive and negative 3. Now, when it comes to talking about vertical asymptotes, that's going to be where your vertical asymptotes are going to be. So that's going to be at x equals positive 3 and at x equals negative 3. So this is going to be our two vertical asymptotes. Okay? Now, to talk about how to find horizontal asymptote, right? Okay, so our given expression is x minus 1 over x squared minus 9. Now remember what I showed you in the example before this. To find the horizontal asymptote, we take the highest degree for our x variable and divide each term of our rational function by that degree. So you can see we have x to the first power on the numerator and x to the second power in the denominator. So x to the second power is the highest power of x, so that's what we're going to take. So I'm going to take my x, divide that by x squared. This is from my numerator. Then I have minus 1. So I'm going to take that 1, divide that also by my x squared. Then we move down to our denominator. We've got x squared. So we take x squared divided by x squared minus 9. So we're going to take that 9 and divide it by x squared also. So basically each term, positive x, this 1 over here, of course we keep the same minus signs in the middle, this x squared term here and this 9 term here, each one of them gets divided by your x squared in this case. Now we want to simplify this, right? So x squared goes into x squared, one time. So these guys will cancel out and become just a 1. On the numerator, x goes in itself, x divided by x squared. One of those x's will cancel out, leaving you with 1 over x, right? So if we just clean this up, I have 1 over x minus 1 over x squared from my numerator. The x squared and x squared canceled out, giving us 1. And then, of course, we still have the minus 9 x squared left behind. Now think about it. As x gets really, really large, all of these expressions that have a number on the top and x on the bottom are going to start getting really, really close to 0, which means this expression's value is going to start getting closer to 0. This expression's value is going to start getting closer to 0, and same thing here. 9 over x squared will also get very close to 0. So when that happens, you will be left with 0 minus 0 on the top, 1 minus 0 on the bottom, which will actually end up becoming 0 over 1, which is the same thing as 0. So that actually tells us that our horizontal asymptote is actually going to be at the line y equals 0, which actually also happens to be the same thing as your x-axis. So this is where you will find the horizontal asymptote for this function. So I hope you can kind of see with this example how we find the vertical and the horizontal asymptotes. Okay? Now one thing you want to make note of is this little paragraph right here. So we are saying when the degree of the numerator in your rational function is less than the degree of the denominator, your x-axis is always going to be your horizontal asymptote, which your x-axis also happens to be the line y equals 0. So whenever the numerator has a degree which is less than the degree of the denominator, you're going to have x-axis as your horizontal asymptote. And you know, that's the same thing that happened here in example number 2. Because the degree of our numerator is less than the degree of our denominator, we got y equals 0 or x-axis as the horizontal asymptote. Now they are telling us for a second type of a problem, if the degree of the numerator is equal to the degree of the denominator, then your x-axis is actually not the horizontal asymptote. In that case, it's actually going to be the ratio of your leading coefficients, and we'll talk about that here in a little bit. So we've talked about horizontal asymptotes, we've talked about vertical asymptotes. Now let's talk about oblique asymptotes, or some textbooks call it a slant asymptote. So of course that means it's not going to be a vertical or a horizontal line, right? That's what a slant or an oblique means. Now, to be able to find oblique asymptotes, you either have to use long division or you have to use synthetic division. It actually just depends what number you are dividing by, because in some cases synthetic division may not work. So you actually just kind of have to think about how oblique asymptotes work. So let's talk about how we can find all the asymptotes for this example here, and then I'll show you how the oblique works. So we've got 3x squared minus 4 divided by x minus 1. So let's see how we can find these asymptotes. Let's start with the vertical one again. Actually, that should be just one asymptote. Alrighty, so remember, for vertical asymptote, you just take the denominator, set it equal to 0, and solve for x. So we'll start by adding 1, and you of course end up getting x equals 1. So this is where we have our vertical asymptote. Okay, now let's talk about how to find the horizontal asymptote. Okay, so horizontal is going to be, let me write this down. So this is where, remember how we tried the highest power of our x and then divided everything by it? So we're going to try and use that same technique here. So I've got 3x squared, and of course between x squared and x squared is the highest degree in this case, so we divide everything by x squared. So we've got 3x squared divided by x squared minus 4 over x squared, and then on the denominator same thing, x divided by x squared minus 1 divided by x squared. So 3x squared and the x squared in the denominator, those x squares will cancel each other out, right? 4 over x squared will stay the same. Then on the denominator, one of these x's will cancel out, so this x goes away with one of the x's on the denominator, and then 1 over x squared, of course, will stay the same. So this will end up giving us 3 from that first term, minus 4x squared from the second one, and then on the denominator we have 1 over x left behind, minus 1 over x squared, right? So just like we saw in the previous examples, 4 over x squared will start going to 0 as x gets really large. 1 over x squared will also start going to 0, and then of course 1 over x will also start going closer to 0. So you're actually going to end up getting 3 minus 0 over 0 minus 0, which is 3 over 0, and that is undefined, right? Anything divided by 0 is undefined. So this actually tells us that there is no horizontal asymptote for this rational function. So we have a vertical asymptote, no horizontal asymptote. Now let's talk about finding the oblique asymptote, okay? So let's look for the oblique asymptote. So I'm actually going to show you how to do this both with long division and synthetic division. So let's start with long division. So you have 3x squared minus 4, which is being divided by x minus 1. So you're going to write this as x minus 1 as our divisor. 3x squared minus 4 as our dividend. And of course you can see we have the x term missing, right? You're going from x squared, there's no x term, and then you're going to negative 4, so that's why I'm leaving that little gap in the middle. So I have 3x squared here, and I only have x here, which means I definitely need the number 3. And to make this x into x squared, I need another x term, right? So we multiply 3x times x is 3x squared. Negative 1 times 3x is negative 3x. And then remember we subtract all of this, which means this guy will end up becoming negative 3x squared. This guy here will end up becoming positive 3x. Okay? So positive 3x squared, negative 3x squared will cancel each other out. Bring down the positive 3x and bring down that negative 4. Okay? So we have 3x over here, just an x over there, which means we're going to put a positive 3 up here, right? So 3 times x is 3x. Negative 1 times 3 is negative 3. Then again we subtract these guys. So this guy here will become negative 3x. This guy here will become positive 3. And then positive 3x, negative 3x will cancel out. Negative 4 added with positive 3 will of course give you a remainder of negative 1. Okay? So you will see when we actually go through the long division, you can actually rewrite your original polynomial, 3x minus 4 over x minus 1. You can actually rewrite it as your quotient, which is the 3x plus 3. And then taking your remainder, you can write it as negative 1 over x minus 1. Since you had the remainder left over, you have to write it by including the divisor, so you write it as negative 1 over, it should actually be x minus 1, like that. Okay, anyway, so this is just how to rewrite it, but now which one is your oblique asymptote? So your oblique asymptote actually is going to be just the quotient part. So the oblique asymptote here is going to be the line y equals 3x plus 3. So this is our oblique asymptote. Okay, this was just rewriting the original expression. So this is not the answer, just the quotient is. Now if you wanted to use synthetic division, for synthetic division we would be taking our expression, which is going to be 3x squared, 0 for the x term, and minus 4 for the constant term. And you're dividing this by x minus 1, right? So remember I talked about this, how you need to change the sign since it's given to you as x minus 1. So 1 itself is a positive number, so you're dividing by 1. Bring down that leading 3. 3 times 1 is 3. 0 plus 3 of course is 3, and then 3 times 1 will be 3. And you get negative 1 as your remainder. So this here is our remainder, which is of course the same remainder we got here, right? And then this here makes our quotient, and of course you can write that quotient as 1 degree less than the original function. So if the original function was x squared, this will be 3x plus 3. And of course this here was our quotient, and you will see it comes out to be the same. So when you are writing the oblique asymptote, it's going to be that quotient, y equals, and it's always y equals, okay? Y equals 3x plus 3 for your oblique asymptote. So this might be something to kind of keep in mind, that functions that have oblique asymptotes, they will not have horizontal asymptotes. If functions have horizontal asymptotes, then they will actually not have oblique asymptotes. So you will have one or the other, but for most part, you can have a vertical asymptote for most functions. Okay? Alrighty, so this was our example number 3 to see how we could find our vertical, horizontal, and oblique asymptote. Okay? Alright, so another thing I wanted to talk about was, like in this function, you can see the degree of our numerator is 1 greater than the degree of our denominator. So basically what happens is when the degree of your numerator is going to be larger than the degree of your denominator, your rational function will actually have an oblique asymptote. And of course the degree on the denominator has to be at least 1. So they're saying you can use the division to rewrite your function as quotient plus remainder over divisor. And this is what I was showing you right over here. So this is how you rewrite your function: quotient plus remainder over your divisor. And then they're just saying get your equation by taking y and setting it equal to the quotient for your oblique asymptote. Okay. Alright, so let's kind of look at the different types of asymptotes we have here. So you have your function f of x equals p of x over q of x. And again, we are assuming these are in lowest terms and the degree of your denominator q of x is at least 1. Okay? So take that denominator, set it equal to 0 to find your vertical asymptote. Okay? For your horizontal asymptote, if the degree of the numerator is less than the degree of the denominator, then your x-axis, which is the line y equals 0, is going to be the horizontal asymptote. If the degree of your numerator is equal to the degree of your denominator, then your horizontal asymptote is actually going to be the ratio of your leading coefficient. So basically they are saying if the degree for both numerator and denominator is the same, just take whatever are the coefficients for your numerator and denominator, right, the leading coefficient, and it's going to be the ratio of those two values. And I think we're actually going to be seeing an example for that in one of our examples here, I believe. Okay? If not, we'll definitely talk about it with our other examples. And then lastly, if the degree of your numerator is greater than the degree of the denominator, then of course you're going to have an oblique asymptote. Okay? And of course remember that you can rewrite those expressions as quotient plus remainder over divisor. And then your oblique asymptote is going to be y equal to the quotient. So you can use long division, you can use synthetic division. Synthetic division, just be careful that as long as you are not dividing by 0, you are going to be okay. Alright, so your oblique or slant asymptote happens in part 4, where the degree of the numerator is at least 1 larger than the degree of your denominator. Okay, now we're going to try and put all of these concepts together to see how we can graph our rational function. So we're going to be using asymptotes, and of course we're also going to be talking about symmetry for these rational functions. So just as a procedure here, start by finding your asymptotes. Now even though these are imaginary lines, to help us with our graphing process, we are actually going to draw them as dashed lines, not solid, because again remember these are asymptotes, so we don't want them to be solid lines because that's what our graph is going to be. So dashed lines for the asymptotes. Again, check for symmetry. It always helps to find intercepts. If we don't have enough aspects or characteristics to draw our graph, we can also find more points to help us get a better idea. And then of course the final thing is drawing our graphs and then making sure they get closer to your asymptotes. But remember, they don't touch the asymptotes and they don't cross the asymptotes. Okay, so we are actually back at the same function that we did for examples 1 and 2, x minus 1 over x squared minus 9. So those were our examples for 1 and 2. So we already know what the domain of this function is going to be. We already know what the vertical and horizontal asymptotes are going to be. So instead of recalculating them, I'm just going to transfer this information over to example 4. So let's write this down. We have vertical asymptotes, and in this case we did have 2 of those, at x equals positive 3 and x equals negative 3. We have horizontal asymptote at y equals 0, which again remember is the x-axis, and we also know that the domain for this function is going to go from negative infinity to negative 3, union from negative 3 to 3, and union from 3 to infinity, right? So just bringing that information over from our examples 1 and 2, okay? So that was basically part 1, where they were asking us to determine the asymptote. So we've already done that. So let's go to part 2, which is checking for symmetry, and then we'll talk about finding the intercept. So let's look for symmetry. So in this case, you can of course see we have a odd exponent on x on the numerator and even exponent on the denominator. So just by looking at exponents, it will not work. So this is where I would recommend actually substituting your x with negative x and see what you get. So this will end up giving us negative x minus 9 on the numerator, negative x squared, so negative x times negative x will become positive x, and you'll end up getting positive x squared minus 9. So we definitely did not get the original function, right? So this is not equal to our original functions, which means this is not an even function. For it to be odd, it would have had to make the entire function negative. So if I would just put a negative sign in front of my original function, that would be negative. And you can kind of write it like this. So that would end up becoming negative x plus 1, because of course we'd need to distribute this negative sign, right? And this is also not the same thing as this guy, right? These guys are not the same function because you have negative x minus 1 for the first one, and this guy is negative x plus 1. So since these two are also not equal, that tells us this is not an odd function either. So since it's neither even nor odd, and of course these are rational functions, that tells us there is actually no symmetry in this graph. Okay, so symmetry didn't work. Let's see if we can find our intercepts. So let's start with, let's put this in color so it'll be easy to stand out. And we've got our vertical, horizontal, and domain here. Alright, now let's talk about our x-intercept. So x-intercept is where you make your y value 0. So that means we will take x minus 1 over x squared minus 9 and set it equal to 0. So the first thing we're actually going to do is go ahead and multiply both sides by that denominator. So multiply both sides by x squared minus 9. So these guys will actually cancel out, leaving you with x minus 1 here. 0 times anything is always going to be 0. So of course you still end up with 0 here. So just take the plus 1 and get x by itself. So you actually have an x-intercept at the ordered pair 1, 0. Okay? Now, let's see if we can calculate the y-intercept. And this is where we make the x value 0. So you're going to have 0 minus 1 over 0 squared minus 9. So of course that gives us negative 1 over negative 9, because the zeros will just go away. Negative and negative becomes positive, giving us a y-intercept at 1, 9. So that's actually going to be the ordered pair 0, 1, 9. So we do have an x-intercept and we do have a y-intercept, right? So this is our x-intercept, our y-intercept. So we're done with the intercepts. Then they said if you need to have more points to help you out, you can add more points. So I am actually going to create a table for our x and y values here, and looks like I am actually going to be using -5, -4, -3, -2, -1, and then 0, 1, 2, 3, 4, and 5. Okay, so if you put these values in your function for the x, just be careful because you may need to do this by using parentheses so that you can get accurate answers. So when we put in -5, you're actually going to get, if you write those as fractions, it's going to be -3/8, or it actually comes out to be -0.375. Excuse me. If you do -4, -4 actually comes out to be -5/7, which will be -0.7 as decimal. So, you know, these guys are going to just give us an approximate location. Obviously, you can see these are not going to give us great locations. When you do -3, remember -3 was part of our vertical asymptote, or where the domain was not defined, right? So this is actually where you're going to get an undefined answer. And that's actually going to be the same thing for +3, because +3 also is one of our vertical asymptotes. For -2, we are actually going to get +3/5 as our answer. So that actually comes out to be 0.6. For -1, we actually get 1/4, which of course is 0.25. For 0, and we just did that calculation, this is where we have our y-intercept. So that's going to be 1, 9. At +1, we have 0 because that's our x-intercept, right? So those are our x and y-intercepts. At +2, we will actually have -1/5, which will be -0.2. And then, of course, +3, we've already talked about that. +4 comes out to be 3/7, which will be 0.42. And +5 will also be 1/4, so that will be 0.25. So you can see all of these are obviously, as I call them, not happy numbers, but they will at least give us an approximate idea of where we need to graph our functions here. Okay, so let's go ahead and get our little grid going. Oops. Let's see if I can move him down here a little bit. Okay, I think this should be good. Okay, so we are going 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And these values are of course going to be our decimals. Let me go ahead and write this 1/9 also, so we know this is going to be repeating ones. Yeah, looks like they're all going to be just between +1 and -1. Okay, now the other thing we want to do is draw our vertical asymptotes, and remember those were at -3 and +3. So remember, we're going to draw them as dashed lines. So at +3, what did I do? I'm not sure what I did here, guys. Hold on a second. Okay, there we go. So at +3, these are vertical asymptotes, right? And then at -3, so it'll be here. Okay, so vertical asymptotes, and then remember, we also have a horizontal asymptote at our x-axis. So using the same black color, I'm actually going to just above the x-axis do these little dotted lines, so that I will remember that my x-axis is also a horizontal asymptote, right? So something like this. And then let's see, we know we have no symmetry in this graph. We have our x and y intercepts at 1, 0. So let's see, at 1, 0 is our x-intercept, which is this point right here, and then that 0, 1/9, which is 0.11111. So right here, very close to the x-axis, is our y-intercept. And then using our other points, let's see what we can do. So at -5, we are at -375, so it will be just a little bit more than a quarter on the negative side. At -4, you are at negative, so 0.7, so just about 3/4 of the way through. Of course, you are undefined at -3. So what's happening here, as you can see, this here is kind of going down this way. So what's going to happen is this arm is going to get really close to this vertical asymptote, but remember, it's not going to touch, it's not going to cross, and then this part here will get closer to that x-axis, and again, it's not going to touch, it's not going to cross, so you're going to have this kind of shape here. Now, on the other side of -3, we have for -2, 3/5, so 0.6. So that's going to be just a little bit more than halfway. At -1, you are at 1/4, so that's again kind of closer to our x-axis here. Then, of course, I've got our y-intercept and x-intercept, so basically I have graphed all of these points so far. So now I'm moving on to +2, which is at -1/5 or -0.2. So again, pretty close to a quarter, and that should be negative. So of course it's going to be below the x-axis, right? So what's going to happen here is, again, this arm of our graph is going to come down here like this, get closer to this vertical asymptote, again, not touch, not cross, and then this arm here is going to cross at the y-axis, then come to all of these points, and then here it's again going to get closer to that vertical, get closer to that vertical asymptote, not touch, not cross. You will see, however, that our graph is in fact crossing the x-axis here. So only with the x-intercept, it is possible for your graph to cross at one point or 2 points, just depending on what kind of graph you have. So with the x-axis is our horizontal asymptote, but with the horizontal asymptote, your graph can actually cross that horizontal asymptote, but it will not happen with the vertical or the oblique asymptotes, okay? Alright, so we got this point, we've got undefined at +3. Then at +4, we were at 0.42, so just a little bit under half. and then we are at 1/4 at positive 5, so getting closer to the x-axis. So this one here is actually going to be, this part gets closer and closer to your horizontal asymptote without touching or crossing it. And then this arm will get closer to the, not again, is going to get closer to the vertical asymptote, again not touching and not crossing it. Okay, so you can see that everything that we had discussed is showing up here. We've got our vertical asymptotes at x equals -3 and x equals +3. So those would be these lines here, x equals -3, x equals +3. So these are the vertical asymptotes. We've of course got our horizontal asymptote at y equals 0, which is the x-axis. There's of course, you can see no symmetry on this graph, and additionally you can see where our points are crossing, and of course we got all of these points graphed. And you can verify your domain. It goes from -infinity to -3. We stop because of the vertical asymptote. Then we go from -3 to +3, and again we stop for the second vertical asymptote, and you pick up at +3 and you go to +infinity. So you can verify your domain here. And then if we had to talk about the range of this function, then the range of this function, even though it is in pieces, if you just look at that center piece, you can see that one arm is going up towards +infinity, the second arm is going towards -infinity. So just by looking at that, you can see that the range of this function will be negative to +infinity. But even if you look at that leftmost part of the graph, that arm is going down to -infinity. If you look at the rightmost part of the graph, that arm is going up to +infinity. So even those arms can tell you what your range is going to be. So just something additional for you guys to kind of think about. Alrighty, so that's our graph for example number 4. And again, you can see these graphs are not going to be very straightforward just because these functions are so different than what we have talked about before. Alright guys, so our next example here is going to be f of x equals x over x minus 2 squared. Okay, so let's take a look at this guy here. So of course we need to find the asymptotes. We want to talk about symmetry, the intercepts, and then of course if we need any additional points. So let's start with vertical asymptotes. So take your denominator, set it equal to 0. So we're going to do x minus 2 quantity squared, and of course to get rid of the square we need a square root, which gives us one positive, one negative root. Square and square root cancel out, giving us x minus 2 equals 0, because again remember 0 does not take a positive or a negative sign. Then just add the 2 and we end up getting x equals 2 as our vertical asymptote. Now here, if you expand that denominator, you're actually going to get an x squared function on the bottom. So you can see I have degree of 1 for the x on the numerator and a degree of 2 for the x in the denominator. So in this case, since the degree on our numerator is less than the degree on our denominator, you're actually looking at option number 2 over here, which says that if the degree of the numerator is less than the degree of the denominator, then your x-axis is your horizontal asymptote. So you can actually just use that little definition that's given to you there to find the horizontal asymptote here. So horizontal asymptote will be degree of numerator is less than degree of denominator. So y equals 0, or the x-axis, is the horizontal asymptote. Okay, so y equals 0. And there you go. Alrighty, not too bad. Now, we of course want to talk about the symmetry for this function. So if we did our original function and replaced it with negative x, that would give us negative x over negative x minus 2, and then the quantity squared will actually end up giving us negative x over negative x minus 2 to the second power. So you actually don't get the original function, and you also don't get the negative of the original function. So it's not the function we started out with, so it's not even, and it's also not the negative of the original, because if you just put a negative sign in front of the original function, it would make the x on the numerator a negative, but not the x on the denominator a negative, right? And we do have a negative on our denominator x, so that's why you're not going to have odd or even functions, and that actually tells us this guy has no symmetry. Okay. Alrighty. Now let's see if we can find the x and y intercepts. So x-intercept, make your y value 0. You will end up getting x over x minus 2 squared equal to 0. And then, of course, we are going to take both sides and multiply it by x minus 2 squared. They cancel out on the left-hand side, and we end up getting x equals, again, 0 times anything is 0, so x equals 0. This will be the ordered pair 0, 0. So that's going to be our x-intercept. For y-intercept, same thing, make your x value 0. So this will end up becoming y equals 0 over 0 minus 2 squared. So that's 0 over negative 2 squared, or 0 over 4, which actually still ends up giving us 0. So that's also the ordered pair 0, 0, which is expected, right? If you got 0, 0 for the x-intercept, then you know it's going to be the same point for the y-intercept. So you're actually looking at the same point for both x and y intercepts here. Alrighty, so let's see what points can we gather to come up with a graph for this one here. So how about we use negative 3, negative 2, negative 1, 0, 1, 2, 3. Maybe a couple more points. Alrighty, so let's see what we end up getting. So we've got negative 3, and let me see what these answers come out to be, okay? Okay. So as you can see, these will be the values for your y value. So at negative 3, you have negative 3 over 25, or negative 0.12. Negative 2 is, of course, negative 1/8. Negative 1 gives you negative 1/9. 0, 0 is, of course, where we have our x and y intercepts, right? And then we've got positive 1, positive 1. At x equals 2, remember that's where we have our vertical asymptote, so that's undefined. And then you can see we've got positive 3, 3, 4 and 1, and then for 5 we have 5, 9. So now let's take a look at what this graph will end up looking like. Okay. So let's see. Got 1, 2, 3, 4, 5. 1, 2, 3. And then we've got 1, 2, 3, 4, 5. Right? Negative 5 here. Okay. So let's put all of this information on our graph now. So first, again, we want to start by marking our horizontal and vertical asymptotes. So that's going to be at x equals 2 for the vertical. So again, remember these are dashed lines since they don't really exist. And then we had our horizontal asymptote again at y equals 0, or our x-axis. Okay, so we've got our lines marked. So now let's try and put some of these points here. So we've got 0, 0, 1, 1, positive 3, positive 3. You've got 4 and 1, and then at 5 you're at about 0.555 repeating, right? So about halfway there. Okay, so what's going to happen on this side is, again, these points will connect, and then this arm will get closer to your x-axis, but no touch. It won't touch it or cross it. And then this arm will of course get closer to that vertical asymptote without touching it or crossing it. Now here we've got 1, 1, 0, and then for negative 1 we are at negative 1, 9, so negative 0.111, so pretty close to the x-axis on the negative side. At negative 2 we are at negative 1, 8, so just a little bit below that. At negative 3 we are at negative 0.12, so you're actually getting closer. So what's going to happen here is you are actually going to be going towards the vertical asymptote here, like this. Okay. And then you're going to cross the x-axis, you're going to come down here, and then you are actually going to start getting closer to that horizontal asymptote over there. Okay, so again we've got our x equals 2 as our vertical asymptote, y equals 0 as the horizontal asymptote. You can again verify your domain for this function, which I don't think we really talked about this. No, we did not. So if we had to talk about the domain for this function, it would be from negative infinity to 2, and then we would go from 2 to infinity, but we cannot include 2 because that's where our vertical asymptote is going to be, right? And then as far as the range goes, it's actually going to be a little difficult to figure out what the lowest point on our y-axis is, because, you know, obviously we haven't calculated every single point. I mean, we can see for the arms that go up, they are going towards positive infinity, but this lowest value on the y-axis is going to be a little bit difficult to calculate, so we're not going to worry about the range for this function, but definitely you want to calculate the domain for this. Okay, alrighty, so that was our graph for problem number 5. Okay, alright, let's take a look at this little paragraph here. So we're saying the graph of a rational function cannot cross a vertical asymptote but it can cross a non-vertical asymptote. So actually, previously I had mentioned it could not cross an oblique asymptote, but by this statement, it seems like it can cross an oblique or a horizontal asymptote. It just cannot cross the vertical asymptote. So vertical asymptote is definitely something we want to remember. Okay. So they are saying for rational functions, of course, what kind of behavior your graph does at the asymptotes is going to be a very important feature for these graphs. Now, this example 6 over here, 3x squared minus 4 divided by x minus 1, is the same example that we had talked about in example number 3, where we found the vertical, horizontal, and oblique asymptote. So it's actually that same example that we are bringing back for the graphing. So this is the same example here, number 3, that we found the vertical, and of course it had no horizontal asymptote, and then we found the oblique asymptote for this. So again, for our problem number 6, I'm just going to transfer that information over. So just get your answer for problem number 3. Vertical asymptote for this graph was at x equals 1. It had no horizontal asymptote. Okay, and then the, oblique asymptote was going to be the line y equals 3x plus 3. Okay, so this is all from our example 3. So, of course, we want to then look at the next thing, which would be symmetry. So replace your x with negative x, which will end up giving us positive 3x squared minus 4 over negative x minus 1. So of course, this does not look anything like the original function, so it's not going to be an even function. And it is actually also not equal to the negative of the original function, because again, if I put a negative on the original function, it should give us negative 3x squared, positive 4, and x minus 1 on the bottom, which is of course nothing to that effect. So this is actually not an odd function either, which again tells us this guy has no symmetry. Okay? No symmetry, which means we can move on to finding our intercepts. So again, we'll start by finding the x-intercept by making the y value 0. So 3x squared minus 4 over x minus 1 equal 0. We start by multiplying both sides by x minus 1. So these guys cancel out, leaving us behind with 3x squared minus 4 equals 0. And now, of course, you want to get x by itself. So we start by moving the 4, then divide both sides by 3, which will end up giving us x squared equals 4/3. And then to get rid of the x squared, will be square roots, which will give us the positive and negative root. And of course, if you simplify this, square root of 4 becomes 2. Square root of 3 will stay as it is. But we can't really leave a square root on the bottom. So we rationalize our denominator. And you end up getting x equals plus or minus 2 square root of 3 over 3. So of course we'll need to find decimal approximations for these guys, but as ordered pairs for our x-intercepts, these guys will be written like this. Positive 2 square root of 3 over 3 comma 0, and then again same thing with negative square root of 2, negative 2 square root of 3 over 3. So let's go ahead and find their decimal approximations. So for positive 2 square root of 3 over 3, this guy is going to be approximately 1.155. Hold on. Okay, and then let's see what is the approximation for the negative. Of course, it's just going to be negative 1.155, right? So at least it gives us an idea of where we will need to graph these points at. So we have our x-intercepts. Now let's talk about finding our y-intercept by making x 0. So that would be 3 times 0 squared minus 4 over 0 minus 1. 3 times 0 squared will of course become 0, so that will leave us with minus 4 on the top. 0 minus 1 is negative 1, which actually just ends up giving you positive 4 over 1, or positive 4. So our y-intercept is going to be 0, 4. And then of course these guys here were our x-intercepts. Oh well. Okay. So let's take a look at what this graph ends up looking like. So let me go ahead and get our little grid over here. And then we have x and y. And so I'm actually going to start by drawing our asymptotes first. And you can do the x and y table here, but this one actually has a pretty peculiar shape, so I didn't need to do our x and y table, but we definitely can do that. Okay, so our vertical asymptote is at x equals 1, which is going to be this line right here. And then remember, your oblique asymptote is the line y equals 3x plus 3. So oblique is y equals 3x plus 3. So that's going to be basically your slope-intercept form. So you can start at positive 3. And you can go 1, 2, 3 down and 1 left. If you wanted to go 3 up and 1 right, you can do that because you guys will have a bigger grid than what I do. But just using these 2 points, we should be able to come up with a line for our oblique asymptote. So it's actually going to be, again, remember, these are dotted lines. Something like that. Okay. And so what happens here, and again, like I said, we can do a little table if it helps you kind of visualize. So you can do, oh, and I just realized my line is a little off over here. This should actually be coming down like this. And something like that. Oops. Okay. Alright, so I'm actually going to use negative 3, negative 2. We can do negative 1. We can do 0, positive 1, positive 2, and positive 3. So So these guys will come out to be. Okay, so you can see we have our y-intercept in there, we have our undefined, and then the other values, and then of course we want to use these x-intercept values also. So this is positive 1.15, so just a hair after positive 1, and then you also have negative 1.15, which will be again just a hair before negative 1. At 0, 4, we have our y-intercept, and then using these other points you can kind of get an idea. So at negative 3 we have negative 5 3/4, so somewhere over here approximately. Oh, sorry, wrong direction. Negative 3 is negative. It'll be somewhere over here. Negative 2 is negative 2.66. So just a little over 2.5. Again on the negative side. Negative 1 is positive 1/2. So right over here. So what's going to happen, and I'm not sure how well I can draw this, but it should look okay. It's a little not really working out how I want to, but I'm going to try. And so you're basically going to follow along this oblique asymptote. Kind of like this. And then you're going to hit that vertical asymptote right here. And so your graph is going to turn slightly and start going up vertically. So kind of like this. And then of course this arm will just keep going, just keep going down like this. Okay? Yeah, these graphs are not the easiest ones to draw. And then on the other side, so we got all of these points taken care of. We've got 2 and 8. I didn't really graph all the way there. And then 3 at 11.5. So what's actually happening here is this arm of your graph will keep going up straight along this vertical asymptote. And then as it hits that oblique asymptote, it's going to change direction and start going this way. So it's going to turn. And then this arm will actually just keep going down, following along the vertical asymptote. Okay? So like I said, this is a pretty peculiar shape for our graph here. Now let's quickly talk about the domain of this function. So your graph is actually defined for all parts of your domain except for where we have the oblique asymptote. So that's going to be at positive 1. So negative infinity to 1, and then 1 to infinity. Now for this function, the range is not going to be too difficult to talk about, right? Because you can see both arms of our graph are headed up and down. So that means the range of this function is going to be from negative to positive infinity. So not too bad. But just another example to kind of show you how the graphing of these rational functions work out to be. Okay. And then we've got one more graphing example before we can look at the rational inequality. So let's go ahead and talk about example 7 over here, okay? Okay, so the first thing we're actually going to do here for example 7 is go ahead and figure out what the domain of our function is going to be. So let's do the domain calculation first. So remember, take your denominator, set it equal to 0, and then you can use factoring or square root property, doesn't matter. So remember, this is again in that form of a square minus b square. So you can factor it into a plus b, a minus b, okay? Difference of squares. Then you take each one of these and set it equal to 0. So subtract 1 here, add 1 here, and you end up getting x equals -1 or x equals +1. So basically the domain will come out to be -infinity to -1, union -1 to 1, union 1 to infinity. Remember, again, you can draw just a number line if you want to visualize this, and then we cannot use -1 or +1 because remember these numbers make our denominator 0. So we can use anything from -infinity to -1, anything from -1 to +1, and then of course anything from +1 to +infinity. So that's what your domain ends up looking like. Okay? Now the reason we calculated the domain first was because we wanted to make sure we knew where our function was going to be, with what numbers were not going to be part of our function value, right? Okay, now what's going to happen here actually is we are going to go back to our function and this one actually, if I rewrite that denominator, I have x minus 1 on the top. The denominator, I can write it as x plus 1, x minus 1. So using that same factoring that I used when we were calculating our domain. So you will actually see that our f function here can be simplified because this x minus 1 and x minus 1 can cancel out, leaving us with 1 over x plus 1. So since actually this function was not in the simplified form and we can simplify this, this actually tells us that we are going to have a little bit of a different graph than what we have seen up until now. So if you actually take this new form of our function, which is f of x equals 1 over x plus 1, and if we try to find the vertical asymptote based on this reduced form of our function, you will actually notice that we only actually have vertical asymptote at one place. So our vertical asymptote is going to be at x equals -1, whereas in our domain, both -1 and +1 are being excluded, but we only have the vertical asymptote at x equals -1. So that means what's happening at x equals 1. So we'll talk about that also. Now, let's talk about the horizontal asymptote. So again, remember when the degree of the numerator is less than the degree of the denominator, your horizontal asymptote is going to be at the x-axis, right? When we saw that in our previous example. So this will be y equals 0 or the x-axis, and that's because the degree of the numerator is less than degree of the denominator. Okay. Alright, so this guy is our horizontal asymptote. So since this guy actually has a horizontal asymptote, that of course tells us we have no oblique asymptote, right? Now if we talk about the symmetry for this function, take your original function and replace it with negative x, and I'm actually just using the reduced form. We're going to get negative x plus 1. So this is not equal to the original function. So it's not even. And it's also not equal to the negative of the original function. So it's not an odd function either. So again, we actually have no symmetry in this graph. So the next things, remember, we want to find out are the intercepts. So to find the x-intercept, we make y equals 0. Oops, sorry. That's going to be 1 over x plus 1 equals 0. Multiply both sides by x plus 1. Alrighty, so let's cancel these guys out. And as you can see, we'll end up getting 1 equals 0 times x plus 1 will be 0. So obviously these are not equal to each other, right? Which actually tells us, that means that we have no x-intercept for this function, okay? That's what that guy comes out to be, no x-intercept. And now let's see if we have a y-intercept and what it is. So for y-intercept, make x 0. And that's going to be y equals 1 over 0 plus 1, which will of course become 1 over 1, which is 1. So y-intercept is going to be at 0, 1, okay? So we have a y-intercept, but no x-intercept. And then to graph our function, see okay, so we are actually going to need a table for this graph to work because we don't have enough information. Now we do know we have domain where it's not defined at -1 and +1. We know our vertical asymptote is at -1, horizontal asymptote is at the x-axis. So let's go ahead and get those in. So at -1, this is our vertical asymptote, and that should be a straight line. Okay. Okay, something like that. And then horizontal asymptote at the x-axis here. Okay. Let's do our little no x-intercept, but we do have a y-intercept at 0, 1, so that will be this point right over here, okay? And let's do a quick table over here. Okay, so for -3, we will have -0.5. For -2, we will have -1. Let's see, +2 is going to be 1/3, which is of course going to be 0.33 repeating. At +3, it's going to be 1/4 or 0.25. And at -1, we know we have a vertical asymptote, so you know it's going to be undefined here. At 0, it's 1 because that's our y-intercept, but I actually want to talk about what happens here at positive 1. So if you go back to the original function, you are actually going to get an undefined answer. But if you take this positive 1 and put it into our reduced function, so 1 over 1 x plus 1, right? You're actually going to end up getting 1/2. But because we know in the original function that this is undefined, because remember when we did the domain, initially we got x equals -1 and +1, which cannot be part of our domain. So what's going to happen is this 1/2 that we are getting over here is actually going to be an open circle, because that means our graph will pass through that, but when it gets specifically to that point, it's going to have a little jump, because it will be undefined at +1. So you're going to go get close to +1, then you're going to have an open circle, so we'll have to jump over that, and then it picks back up after +1. Okay, so let's see what these points end up looking like. At -3, we have -1/2. At -2, it's -1. Of course, we've already got our 0, 1 here. We're putting open circle at 1 and 1/2. And then we've got at +2, it's 1/3. And then at 3, it's 1/4. So you're basically getting closer and closer to the x-axis. So what's going to happen here is we are actually going to have this part of our graph get closer to the x-axis. You have that little open circle here, and then you're going to cross the y-axis, and this will actually go this way and get closer to this vertical asymptote. Right, so that's going to be the shape on that right hand side. And then on the left hand side, you can actually see this guy is going to start going down towards this end. Let me see if I can do that better. Let's see, it'll go down like this. Okay, so keep going down this way, and then here it's going to get closer again to that x-axis and keep going like this. Okay, so that's what this function is going to end up looking like. So again, if you want to check your domain here, you're going from -∞ to -1, because at -1 we are running into the vertical asymptote, right? So that's what's happening at -1. Here, of course, we have our horizontal asymptote, and then right here at x equals 1, we have an open circle. So that's why your domain goes from -∞ to -1, then right after -1 to +1, and then of course from +1 to infinity. Now, if we have to talk about the range for this function, you can obviously see, since we have that horizontal asymptote and our graph is not crossing that horizontal asymptote anywhere, so our range will actually end up going from -∞ to 0, because at 0 we have our horizontal asymptote, and then union from 0 to infinity. So this is again mainly because our graph is not crossing the x-axis. That's why we have to make sure we do not include 0 in the range of our function. Okay, So these were all the graphing examples that we wanted to talk about. Now the very last thing we want to talk about is the rational inequalities. And again, they're asking us for the first one to use the graphing of the graph of the function to help us. So basically here the idea is this is going to be very similar to what we did with quadratic inequalities, and then of course the polynomial inequalities in the last section. And if you actually look at example number 8, when we try graphing this, it is actually going to be very, very similar to what we just got done with example 7, because they are the same type of a rational function. Okay, so let's go ahead and take a look at what the graph for this function will look like. Okay, so this is number 8. Again, remember we start by talking about the domain first. So take your denominator, set it equal to 0. This factors into x plus 2, x minus 2, just like for our difference of squares, a square minus b square, right? So each one of these, set it equal to 0, subtract 2, add 2. So these guys cancel out, leaving us behind with x equals negative 2 or x equals positive 2. So again, if you think about these in terms of number line, we cannot include negative 2 and positive 2 in our domain, but everything else is going to be okay. So the domain is going to go from negative infinity to negative 2, union negative 2 to positive 2, union positive 2 to infinity. Okay? Now we are ready to reduce this function. So we take our original function, x minus 2 over x squared minus 4. Again, I'm going to factor our denominator just like we did with our domain right here. So x plus 2, x minus 2. And again, you will see that x minus 2 and x minus 2 cancel out, leaving us with 1 over x plus 2. Okay, so this is now our function. And when we try to find the vertical asymptote for this guy, take your denominator, set it equal to 0, and of course you will end up getting x equals negative 2 as the vertical asymptote. For horizontal, it's going to be the same rule. Since the degree of our numerator is less than the degree of our denominator, y equals 0, or the x-axis, is going to be our horizontal asymptote. Okay? Okay, now that we have found our asymptotes, let's talk about symmetry. So we take f of negative x into our reduced form, which will end up giving us 1 over negative x plus 2. So that's not the original function. That's not the negative of the original function. So again, it's not an even function. It's not an odd function, which means this guy also actually has no symmetry. Now, it's not true that all rational functions don't have symmetry, but it looks like all the examples we looked at didn't have any symmetry, but your rational functions can have symmetry. We just haven't come across any of those examples yet. Okay, intercepts. So again, we'll start by calculating our x-intercept by making y equals 0. So you'll take 1 over x plus 2, set it equal to 0, multiply both sides by x plus 2. So again, same thing like we saw in the previous example, you end up getting 1 equals 0, which is not true. So that tells us we have no x-intercept. Okay. Now let's see what happens for our y-intercept here. Make our x value 0. Which will of course end up giving you 1/2. So the y-intercept is actually at 1/2 or the other way, sorry. 0, comma, 1/2. Okay, so that's our y-intercept. And then, of course, the only other thing we want to do now is graph this. So maybe again do a small table to help us out. Okay, so just our basic grid here to help us out. Okay, so let's see what information do we have. At -2, we have a vertical asymptote, so this guy will be undefined. And let's see, at 0, 1/2, we have our y-intercept at +2, which is going to be one of the other numbers that we were not including in our domain. So if you just use that +2 to calculate your point, you're going to end up getting 1/4. So this 1/4, remember again, is going to be an open circle because that point is not going to be defined. Okay. And then let's see what do we get for the other points. At -1, we will get, let's see, that will be -1 plus 2, so that's a 1. So you should get a 1 over here, and you should get a 1/3 over here. So, alright, let's go ahead and do our vertical asymptote, horizontal asymptote. So that's at x equals -2 and the x-axis. So right here, at -2 is our vertical, and then at the x-axis itself is our horizontal asymptote, right? Then at 0 and 1/2, we have our y-intercept. At 2 and 1/4, we have an open circle for our domain where the domain was undefined. So again, we're going to have that little jump. So let's see, at -1, we are at +1. At +1, we are at 1/3. So it may actually help to do a couple more points. So maybe you want to include -3 and -4 in here. So -3 will actually end up giving you -1 over here, and -4 will actually give you -1/2 over here. So you can do -3 is, sorry, wrong direction, -1, and -4 is -1/2. So what's going to happen is this arm of go down this way, right? And then this arm will go up towards the x-axis like this, and then on the other side This guy will go upwards like this. Oops. Kind of like that. And then this one, of course, will get closer and closer to our x-axis here. Okay? So at x equals -2, we have vertical asymptote. Y equals 0 is horizontal asymptote. And then at x equals +2, we have an open circle. So if you again wanted to verify your domain, that would be going from -∞ to -2, union from -2 to +2, and then again from +2 to infinity. If you talked about the range for this guy, it would be -∞ to 0, and then union from 0 to infinity. Okay? Alright, so remember, graphing was just one part of it. We are still trying to solve the inequality. So this one was basically asking us, where is our function going to be greater than 0, right? So let's write that inequality down again. Greater than 0, right? So we're basically saying where is y greater than 0. And again, remember, this is only greater than, right? It's not greater than or equal to. So of course our y value, you can see, is going to be greater than on this part of our graph, right? This portion of our graph is where we can say y is greater than 0, and of course that's going to be for the entire arm. Our y value is going to be greater than 0. So what's going to happen is when you write the solution set, of course you can see we start at the -2 on the x-axis, right? Because this is interval notation. So we're going from -2 to +2, so that's going to be this portion of our graph will go from negative to +2, but then we have to stop right here at +2, and then we'll pick right back up from +2, and of course we'll keep going towards infinity. So it's only going to be going from -2 to 2, and then again it starts from 2 to positive infinity. So for our inequality, our solution set is going to be going from -2 to +2, and of course we're not including our endpoints. And then since I cannot include 2 in there, there's the union, and then we pick right back up from 2 all the way to positive infinity. So this is actually the solution set for your inequality, and they were asking us to do this by using a graph. Okay, so this was example number 8. Alrighty, so they are telling us a rational function can change sign only at a 0 of a function or at a vertical asymptote. So what that means is your rational function can go from a positive to a negative if it actually crosses your x-axis, so if it actually goes to the x-intercept. So on one side of the x-intercept it could be positive, on the other side it could be negative, or it can change signs, so the rational function can give you a positive or a negative value when you are looking at either side of the vertical asymptote. So you can kind of see in this example that we just drew, on the, if you look at that vertical asymptote x equals -2, you can see on the left hand side our function is going to be all negative values, right? So here all our y values are going to be less than 0, but then on the other side of the vertical asymptote, on the right hand side, of course all of our y values are going to be greater than 0. So that's kind of what they're talking about, is that a rational function can change sign only at a 0 or at a vertical asymptote. Okay? Now, how will we use the test point method to solve these rational inequalities? So let's take a look at these steps over here. So they're saying rewrite the inequality, if necessary, with 0 on one side and the ratio of your polynomials, of course, in lowest terms on the other side. So basically the idea is make sure you get 0 on one side and then find all the zeros for your polynomial function in the numerator and denominator. So you're basically going to take your numerator value, set it equal to 0, and then you're going to take your denominator values and set it equal to 0 and find those answers. They're also saying the rational function is undefined at the zeros of your denominator, because remember, that's where you're going to have your vertical asymptotes at. Then they are saying locate the zeros from step 2, so that's this step right here on the number line, and then of course you're going to find your test point from each of those intervals. So locate the zeros from step 2 on your number line, and then pick a test point from each interval, and then of course we're going to be seeing where we find a positive and a negative value for our function. Okay, so we're going to be looking at number 9 over here. So we are given 1 over x minus 1 is greater than equal to 0. So the first thing, of course, we want to do is get 0 on the right hand side, right? So we're actually going to start by taking our function and moving this 1 on the left hand side so that we can get 0 on the right hand side. So you will actually end up getting 1 over x minus 1 minus 1 greater than equal to 0. But I can't just leave it like this, so I have to actually find a common denominator, and we'll end up multiplying this side by x minus 1 and x minus 1. So you will end up getting 1 over x minus 1 minus x minus 1 over x minus 1 greater than equal to 0. Since they are a common denominator, you can actually write this as 1 minus x minus 1. Go ahead and clean that up. Distribute that negative sign. You end up getting 1 minus x plus 1 over x minus 1, which will of course end up becoming 2 minus x over x minus 1. So this is actually what your rational inequality is going to be for. Okay? Now, our step 2 was finding all the zeros for our numerator and denominator. So we're going to take 2 minus x, set it equal to 0, and we're going to take our denominator also and set it equal to 0. So if I just add that x, move it to the other side, and I'm adding the x so that I can make that x into a positive number. And then of course here, we just move that 1 to the other side. Now remember, this is coming from the denominator. So this is our vertical asymptote, and this one of course will be our X-intercept. Okay. Now the idea here is when you are setting up your number line to pick your test points, you're going to use both of these numbers. So we have positive 1 and positive 2, right? So this number here and this one here. So positive 1, positive 2, of course this would be positive and this would be negative infinity. If we had to pick test points from each interval, smaller than 1, you can use 0 over here, something between 1 and 2. Unfortunately, we will have to go with a fraction or a decimal, so I'm going to use 1.5 here, and then something larger than 2, we can of course use 3, and then we want to know what our sign is going to be in each of those intervals. So let's start testing these tests, or I guess checking these test points. So this is going to be in our function, which was 2 minus x over x minus 1. So let's start with the first test point, which is x equals 0. 2 minus 0, 0 minus 1 will end up giving you negative 2. So that tells us all the signs here are going to be negative, right? All the y values are going to be negative there. For x equals 1.5 as our second test point, that's going to be 1.5 minus 0, 1.5 minus 1, so that's of course 1.5 minus, divided by 0.5, and I actually set up my numerator incorrect over here, so let's start this over again. So this guy should be, 2 minus 1.5, and this should be 1.5 minus 1. There we go. So this will give us 0.5 on the top, 0.5 on the bottom. So it's the same number divided into itself, which will actually give you 1, and that's a positive 1. So that means all our y values are going to be positive in this interval. And then our last test point was 3. So that's 2 minus 3, 3 minus 1, which will give us negative 1 over 2, which is basically negative 1/2, right? So again, that means this interval, we are going to have all negative values. So now let's look at our inequality. This was going to be, after we cleaned it up, this guy right here. So this one is of course asking you where your function is going to be greater than and equal to 0, right? Greater than and equal to 0. So remember, and if it helps, you can actually write this down here. We have a vertical asymptote at x equals 1, and we have an x-intercept at x equals 2. So of course, vertical asymptote is not going to be included, right, in our domain, so that's not going to be helpful. So our inequality is asking us where is 2 minus x over x minus 1 going to be greater than or equal to 0, or basically it's asking us where are our y values going to be positive and equal to 0. So right here in this interval, our y values are greater than 0, and then right here at x-intercept, your y value is going to be equal to 0. So when we write our solution set for this inequality, you are actually going to say it's going to be between 1 and 2. Since I have vertical asymptote at 1, I cannot include that. But since I have an x-intercept at 2, I can include that. Okay? So vertical asymptote at 1, so that's why we're putting parentheses of 1. X-intercept at 2, so that's why we are including it. And of course, this is a greater than and equal to inequality, and that's why we put that bracket on top of 2. Okay? So this is what your solution set is going to be for problem number 9, where we are solving the rational inequality. Okay, and then we've got one more example here, which is also using the test point method. So we are given x plus 3 divided by x minus 1 greater than or equal to 0. So since it's already greater than or equal to 0, we of course don't need to rewrite it. So that means we can actually start by finding our zeros. So take your x plus 3, set that equal to 0, and x minus 1, set that equal to 0. So subtract 3 here, add 1 here. These guys will cancel out, giving us x equals negative 3 and x equals positive 1. Now remember, at x equals negative 3, that's coming from the numerator. So this is our x-intercept. X equals 1 is coming from the denominator. So this is our vertical asymptote. Okay? Alrighty. So again on the number line, we are going to put both of these numbers. So I've got -3, +1, of course, positive infinity here, negative here. So again, like I told you, if it helps, at -3 we have an X-intercept, at +1 we have a vertical asymptote. Alright, so from each interval, we need to select our test point. So let's see, something smaller than -3. Of course, you can do -4 or anything else that helps you out. Between -3 and +1, of course, I'm going to select 0, just because I think it's an easier number to work with. And something larger than 1 will, of course, be +2, right? So those are our test points. So let's check them. So again, remember your expression is x plus 3 over x minus 1. So we're checking for test point -4. -4 plus 3. -4 minus 1 will be -1 over -5. So that's a +1/5. So in this interval, all our signs are going to be positive, or basically all our y values are going to be positive, okay? Then our next test point is 0. So let's see, that would be 0 plus 3, 0 minus 1, so that's 3 over -1, or basically -3, which means all the signs here in the middle are going to be negative. And our last test point was +2. So again, this guy will be 2 plus 3, 2 minus 1, so that's 5 over 1, or just +5. So of course, that last interval, all our signs are going to be positive. Now, our original inequality is asking us again, where is our inequality going to be greater than or equal to 0? So greater than equal to 0. So again, we are asking you, where are the y values going to be greater than 0, and where are they going to be equal to 0? So you can of course see in this interval, our y values are greater than 0. In this interval, again, y values are greater than 0. Now at +1, I have a vertical asymptote. Of course, I'm not including that. At -3, I have an x-intercept, so that's exactly where your y value will be equal to 0. So when you write your solution set, it's actually going to go from -∞ to -3, and you will include -3, and then you'll pick it right back up with the union symbol from +1 to infinity, but we will not be including +1 because that's where you have the vertical asymptote. So our solution set is going to be -∞ to -3, and because this is greater than and equal to, because of that middle equal to, we're putting a bracket here where we had our x-intercept, and then union, we start back up from 1 to +∞, because at 1 we have a vertical asymptote, we cannot include 1, right? So that's why we're going to be putting parentheses on +1. Alrighty, so this is your test point method. And again, you can see how much quicker the test point method is compared to our graphing process, right? Okay, so this was your second example for the test point method. And then the very last example that I wanted us to look at here was this application over here. So we're saying rational functions can be can occur in many applied situations. Basically, when we talk about the horizontal asymptote, that can indicate the average cost of producing a product as it approaches a fixed value in the long run, right? So you can kind of think of that horizontal asymptote is where your average cost is going to get closer and closer to as your fixed value will start getting as your average cost will start getting closer to the fixed value. Your vertical asymptote, you can show that the cost of a project will actually keep going up astronomically as a certain barrier is approached. So that barrier would of course be your vertical asymptote. Okay, so there are different ways that these applications can work. The one example we are looking at is talking about a truck rents for $100 per day, plus there is an $80 per mile charge, right? So they're going to charge you $100 for the day, and then depending on how many miles you drive, for each mile is going to be 80 cents, right? Basically 80 cents per mile. So they want us to basically just write a function that gives us the average cost per mile for 1 day of rental. And then what happens to the average cost per mile as the number of miles gets very large. So this is again talking about, when your value will get really, really large. So let's take a look at what this problem ends up looking like. Okay, so they're telling us we are renting this truck for $100 per day plus $80 per mile. And since they are asking us to find the average cost per mile, let's go ahead and say that X is going to be our number of miles that the truck will be driven. Okay, so X represents the number of miles, and we're trying to figure out what the average cost is. So let's call our function C of X, and they're basically telling us that we are going to end up paying $100 for a day, plus we are going to pay 80 cents for each mile, and mile is of course X, right, the number of miles. And since they are saying this is going to be the average cost per mile, you're actually going to divide this entire thing by X also. Okay, so you are actually going to end up getting, and if you want to write this in the standard form, you can write it as 0.80x plus 100 divided by X, or you can leave it how I had it here. It really wouldn't matter. But now, as far as your part 1 of the question goes, which said write a function that the average cost per mile for 1 day, so that's actually going to be this part right here. So that was that first part of the question. The second part was asking what happens when the average cost per mile, what will happen to the average cost per mile as the number of miles gets very large. So they actually now want to know what happens when X gets really large. So when X gets very large, that means you are actually finding your horizontal asymptote. So in this case, what we are going to do then is we are going to take our function, that was supposed to be 0.80x plus 100, and we're dividing by X. So remember when we were talking about finding horizontal asymptotes, you have to take the highest power of your X variable and divide each term by that X, right? So I have X on the numerator, X on the denominator, which means I'm going to divide each of these terms by X. So X and X here will cancel out. X and X will cancel out, giving us 1. So we will actually end up getting 0.80, because these X's canceled out, plus 100 over X, and then just 1 on the denominator, right? And we know when X gets really large, a fraction like this, 100 over X, will start getting closer to 0, right? So that means you will end up getting 0.80 plus 0 over 1, which will of course just become 0.80. So the idea here is, as your X value gets really large, your average cost per mile will actually get closer and closer to just being 80 cents per mile. So you can write this as This is of course dollar amount, so we can say as x gets very large, our function c of x approaches, or basically gets closer, approaches the horizontal asymptote, which is that your cost will start getting closer and closer to 80 cents per mile. So think about this statement a little. Our x represents the number of miles, right? So the idea here is the more distance you drive, the more economical it's actually going to be. So as your x gets really large, your function value is going to get much more economical, which means that you will be paying, like I was saying, less in your per mile charge. Okay, so this is kind of what we are talking about here in terms of how you can use applications for rational functions. All right, guys, so this was our last example here in section 3.5. So again, look through these notes and then let me know if you have any questions, and then of course I will see you guys in class. So have a wonderful day, be careful, and I will see you guys in class. All right, guys, bye-bye.